Question number 76. In which of the following the order of arrangement does not agree with the variation of property indicated against it? Let's check the first property, that is electron affinity, and if we check the given order, oxygen is given firstly, then tellurium, then selenium, and then sulfur it is. And this order is correct here. In this case, oxygen has less electron affinity due to its small size. And due to that, there would be more interelectronic repulsion. That's why there is the anomalous behavior of this oxygen and it has least electron affinity. Otherwise, tellurium, then selenium, and then sulfur, it is correctly given. And on that basis, it is correct, not incorrect. We need to just find out the incorrect order that does not agree with the variation of the property indicated. Now, let's check next property, first ionization enthalpy. If you check the order given here, these are the elements of group 13 and boron has the maximum first ionization enthalpy while indium has the least. If you look at the table, you will identify that boron, due to its small size, has the maximum first ionization enthalpy. Then there is a turn for thallium. After that, gallium is there and then indium. So it's also correct. After that, silicon, beryllium, magnesium and sodium on the basis of metallic nature. If we talk about metallic nature, as we move left to right in the period, metallic nature decreases. Sodium is the element of group 1 while magnesium is the element of group 2. Similarly, if I talk about beryllium, that is also present in the group 2, but down the group metallic character increases. It means magnesium is more metallic as compared to beryllium. Then here is the silicon, that is the element of group 14. So this order is also correctly given. Further, if I talk about the next one, that is the order of ionic radii. Hydride ion, fluoride ion, chloride ion and bromide ion. If you leave this hydride ion, others seems to be correct. But if I talk about hydride ion, that has exceptionally larger size and it should be here after bromide, not here at the first position. So it means this is incorrectly given, and if it is incorrect, then correct answer becomes option 4. Now it's a turn for question number 77. Question number 77. The pair of the species having same bond order is. To identify the bond order of the given species, we need their molecular orbital configuration. Those I have here for you. Just have a look on that. First, we have the configuration for O2. That is having the atomic number more than 16. That is having the atomic number more than 14. So, first shell, K shell, we have already filled. Further, sigma 2s2, then sigma antibonding 2s2. Sigma 2pz2, pi 2px2, that's having the equal energy as that of pi 2py2, 2 electrons are filled here. Further, pi antibonding 2px, it has 1 electron, and pi antibonding 2py, it also has 1 electron. So in this way, we have distributed electrons here. But if atomic number is 14 or less than 14, then we follow the configuration of nitrogen, N2. So that configuration I also have for you. Just have a look on that. First shell we have filled. Sigma 1s2, sigma antibonding 1s2. We have already filled in the form of Kk. Further, sigma 2s2, sigma antibonding 2s2. After that, there would be the turn for pi 2px2, then pi 2py2. And after that, here would be the turn for sigma 2pz, in which 2 electrons are present. This is the configuration for nitrogen. While for other species, also I have written the configuration for you. Now, on the basis of that, you can identify number of bonding electron and the number of antibonding electron. So simply, for the calculation of bond order, we need half of the bonding electron minus anti-bonding electron. Now, let's check in these given species. First, if I talk about the very first species, O2. In this case, there are total bonding electron which are 10. So in this case, bond order becomes equals to half of 10 minus antibonding electron. 2 in K shell, antibonding electron, plus 2, 4, and 2 antibonding electrons are here. Total 6 electrons are there which are antibonding electron. And this way, the bond order becomes 4 by 2, that is 2. So the bond order for oxygen becomes 2. Similarly, if I talk about NO positive, you can calculate. For O2 negative, you can calculate. And if you check all the given species, you will see that the bond order of O2 is 2, as well as this bond order is 2 also for C2. Let's check for C2 also. Bond order is equal to half of the bonding electron. In case of C2, bonding electron 2 in K shell, 4, 5, 6, 7, 8. Total 8 bonding electron minus how many anti-bonding electrons? 2 in K shells. Further plus 2, 4. 4 anti-bonding electrons are present here. So 8 minus 4, that becomes 4 by 2 once again, that is also 2. So bond order for C2 is also 2. Bond order for O2 is also 2, while for other species bond order is not same. So on this basis there are 2 species which have bond order equal to 2. And that's why we can choose option 3 as our correct answer. After this, there is another question. Question number 78. The pair of isostructural species is. We have different pairs given here in which we need to identify the isostructural species, the pair of those type of species. First option SF4 and SiF4. Hybridization of SF4 is sp3d. Sulfur is sp3d hybridized, and in this case we obtain seesaw structure. While in case of SiF4, the hybridization is sp3. In this case, the shape of the molecule is tetrahedral. So this is not our correct answer. After that, the next one, CO2. CO2 is a linear molecule with sp2 hybridization of carbon. Further, SO2, this is a bent molecule, we know that. So that's why these two are not isostructural. Now third option we have ClO3 negative and NF3. If we talk about these two species, hybridization is same sp3. And what about the structure? Both of these have pyramidal structure. I'll just draw the structure for you. Chlorine is here with a lone pair of electron and ClO3 as it is. So this is the structure. While if I talk about the structure of NF3, you know that that is pyramidal structure with a one lone pair. It means these two are isostructural, but let's check the last one also. Now fourth option, XiF2 and I3 positive. If I talk about XiF2, this is a linear structure, while this I3 positive has the bent structure. That's why this is also wrong. So only one option is correct, that's given here in option 3. So I've chosen this. After that, question number 79. Which among the given compounds can exhibit tautomerism? So if I talk about tautomerism, there should always be an alpha hydrogen atom, alpha to the carbonyl carbon, you know that. And if I talk about the first compound, in this case, this compound can be tautomerized as this way because it has alpha carbon this and hydrogen comes here to give you this tautomer. After that, if I talk about the second compound, the double bond cannot exist here at the bridged carbon. So this structure is incorrect, it cannot tautomerize. Even if I talk about the third species, we have this hydroquinone here. In this case, you can clearly see that there is no hydrogen atom alpha to these carbonyl groups. That's why it cannot exhibit tautomerism. After that, the fourth compound. We have this compound and it can tautomerize to give you the phenol in this way. And if it is so, it means first and fourth are showing tautomerism. Where these are given, this is given in option 1, both 1 and 4. So answer for this question becomes option 1. After that, next question is waiting for you. Now question number 80. 0.23 gram of nitrogen containing organic compound was zildalized and ammonia obtained requires 23 ml of M by 10 H2SO4 for neutralization process. The percentage of nitrogen in the organic compound is. Here we should take a simple formula that the percentage of nitrogen in a particular compound, organic compound we're talking about, is equal to 1.4 into the milli equivalence of ammonia. Those are involved here, and further this should be divided by the mass of organic compound this way. Now in this case we need the milli equivalence of ammonia. From where we will obtain them? From the milli equivalence of H2SO4 that is used for the neutralization process. Actually we know that for the process of neutralization the milli equivalence of ammonia should be equal to milli equivalence of H2SO4 that you are taking here, and milli equivalence of ammonia would be equal to its normality into volume. So volume we have 23 ml, and normality we have molarity here 1 by 10. Just multiply n factor for H2SO4, that is 2, and multiply 23. So this is the calculation of milli equivalence of H2SO4. So simply we can write here these are 2 into 23. That can simply be written as 46 by 10 milli equivalents of ammonia you have. Now, if you have this value, percentage of nitrogen can easily be calculated. That would be equal to 1.4 into 46 by 10, and it should be divided by the mass of organic compound. What's that? That is 0.23 gram. It's given in the question. So 0.23. There's a simple calculation. This would becomes 20, and if you solve this for the value, it would be equal to 28%. And if it is so, correct answer is option 2 that you should choose. After that,